Question 1. One of the postulates of special relativity states that the laws of physics are the same in all inertial frames of reference. State what is meant by inertial in this context. Well, we learned in step 1, mass of the majority, that an inertial frame of reference is one that is not accelerating. It does say state, it doesn't say explain, and we're just really looking for the key word to allow us to get that 1 mark. You could have put where Newton's laws apply, or you could have put not subject to an unbalanced force, which of course means it's not accelerating, but I would suggest that the easiest, quickest answer there would be not accelerating. B. An observer is travelling at velocity v towards a light source. Determine the value the observer would measure for the speed of light emitted by the source according to Maxwell's theory and Galilean transformation. Okay, well, I'm going to do the easier one first. I think the easier one is Galilean transformation. So let's think about this light source. It's emitting a light and it emits at speed c. There's a traveller or an observer moving towards it at speed v. And the Galilean transformation is used in classical mechanics and assumes velocity simply add up in everyday experiences. So if the observer is moving towards it with a velocity v, then the Galilean transformation suggests that the observed speed of the light would be c plus v. And that's, of course, harks back to when we did examples in step 1 where a train's moving towards somebody at 50 metres per second, the observer's moving towards it at 5 metres per second, then the Galilean suggestion would be that the observer's observed speed would be 55 metres per second. It's a simple addition. So for C2, it's C plus V. Now back to number 1, which is Maxwell's theory. And the reason I say it's harder is because you might not have heard of Maxwell's theory. So we have to make some sort of assumptions here. Let me tell you a little bit of background. According to Maxwell's equations, the speed of light in a vacuum is always c, which is 3 times 10 to the 8 metres per second. And that's regardless of the motion of the source of the observer. So it doesn't matter what this guy's doing, they'll always see the light travelling at c. And that theory was the underpin of Einstein's theory of relativity. So Einstein used Maxwell's theory to come up with his theories. So actually here, we're always going to have c. Now, you might not have known Maxwell's theory. You might not have understood it, but there's only so many answers you could have given here. And if I hadn't have heard of Maxwell's theory before, and I was thrown with that question, I'd just do what I thought best. Right, what's the speed of light? C, that makes most sense, and pop it down. It's 1 mark. You've answered it. Move on. Question 2. An electron is emitted from a nucleus with a speed of 0.975 c as observed in a laboratory. The electron is detected at a distance of 0.8 metres from the emitting nucleus as measured in the laboratory. A. For the reference frame of the electron, calculate the distance travelled by the detector. Okay, 2 things jump out at me here. 1, this speed is very fast, it's very close to the speed of light. So we'll be looking at finding out what the Lorentz factor is. The second thing is we're looking at distance. So in my mind, I'm immediately thinking we're going to look at length contraction, and I'm thinking that formula is going to be useful for us. Okay, but before we can do that, we have to work out who is measuring proper length and who is experiencing contracted length. Now, proper length is defined as the length measured by an observer who is at rest relative to the object being measured. And in this case, the lab is at rest relative to the frame of the electron. So the lab is experiencing proper length and the electron is experiencing contracted length. L equals L naught over gamma. And gamma, of course, is the Lorentz factor. We've got to work that out. So gamma equals, almost forgot what it was there. 0.975 squared over 1 squared, which is, of course, 1. And if you pop that onto the calculator, you'll get 4.5. So our Lorentz factor is 4.5. We take it here. This is 0.800. divided by 4.5, which gives us a length of 0.1778 meters. Let's have a look at the number of significant figures. The data is given to 3 significant figures, so our answer should be given to 3 significant figures. So our answer here is the distance travelled by the detector is 0.178 meters. B. For the reference frame of the laboratory, calculate the time taken for the electron to reach the detector after its emission from the nucleus. I'm going to do a little aside here, and whenever I'm thinking about time, I always think about the two twins. One twin stays on Earth, and he waves off his twin, and his twin goes at relativistic speeds multiple times around the Earth. We're thinking about this twin on Earth at the moment. He's measuring time as normal. He's got a clock and he's just measuring time as normal. And for him, like, time equals distance over speed. And everything's normal for this guy. This guy who's on the rocket ship, he's measuring his time as normal as well. But for him, he's experiencing proper time because the time interval measured between two events, so say he starts his clock and stops his clock, in his reference frame is at the same spatial location, because according to this guy here, he's staying still. Everyone else is moving. So this guy here experiences proper time. The twin who's left on Earth, he experiences time, but it's dilated compared to the twin who's whizzing around the Earth. So your man on Earth is going to experience time that's measured as normal, time equals distance over speed, but it feels longer compared to your man who's whizzing around the Earth, and he's going to come back younger than the other guy. Okay, so that's our little aside. How does that relate to B? We're looking at the reference frame of the laboratory, and in this case, the laboratory is like the twin on Earth. He's just measuring time as normal. So it's time equals distance over speed. So we've got 0.8 as a distance, and let's see what it says up in the question. Yeah, that's a distance measured in the laboratory. And the speed measured in the laboratory, observed in the laboratory, as it says up here, is 0.975 times 3 times 10 to the 8. Let's put it all into the right units. So that gives us 2.735 times 10 to the minus 9 seconds. And let's make that a bit neater, 2.74 nanoseconds. Now we're going down to C. For the reference frame of the electron, calculate the time between its emission and the nucleus and its detection. Well, the electron is the equivalent to our twin who's whizzing around. They're experiencing proper time. So that's the electron. The lab is time, and that's the lab. So let's find out our equation. T naught equals T over the Lorentz factor. But we want to find out, we want to find out what T naught is. And we know that the time for T naught, the electron, is going to be smaller than the time experienced by the lab. Great, so if we take that time divided by 4.5, it is going to be smaller. Everything's working out fine. Divided by 4.5, which gives us the answer 0.608 nanoseconds. Fabulous. D. Outline why the answer to C represents a proper time interval. Well, we've actually explained that already, but let's write it down. From the electron's perspective, it is the lab and the detector that are moving. Therefore, electron is stationary. Therefore, both events occur at the same position. Which goes to proper time. You could also just say that it's the electron experiences the shortest time interval. And you could put down the formula, T naught equals T divided by lambda. If this is greater than 1, then T naught must be shorter. So you could write either of those two things. Question 3. An observer on Earth watches a rocket A. The space-time diagram shows part of the motion of A in the reference frame of the Earth observer. That means this is the Earth, and this is the reference frame of rocket A. 3 flashing light beacons, X, Y and Z, are used to guide rocket A. The flash events are shown in the space-time diagram. The diagram shows the axes for the reference frames of the Earth and rocket A. The Earth observer is the origin. Okay, we know that, thanks. A. For the reference frame of the Earth observer, calculate the speed of rocket A in terms of the speed of light c. For that, we need to use this relationship here, tan theta equals v over c. We use that relationship to find the speed of another reference frame in relation to an original reference frame using a space-time diagram. It's really, really simple, but I want to show you it from first principles. This is the CT reference frame of the rocket, and we want to measure the speed of that in relation to this reference frame of the Earth. And what we have here, you'll see, is a right-hand triangle. This is theta here, and if we think about tan theta is equal to the opposite length of the triangle over the adjacent length of the triangle. And in this case, this is the opposite, this is the adjacent. So the opposite length of this triangle here is 0.8 kilometers. And the length of the adjacent is 2 kilometers. They're both in the same units, which is great. That means we can continue. Let's go down here. So VC is equal to tan theta, but we already know from tan theta up here that tan theta is equal to 0.8 over 2.0. So it is equal to 0.8 over 2.0. That means that V is equal to 0.8 over 2.0 times C, which is 0.4 C. And it does say we want the answer in terms of the speed of light. So our answer is 0.4 C. Very simple. We didn't have to use the calculator at all. I'm going to clear the graph because I've got a feeling we're going to draw some stuff on this graph in a second. B. Using the graph, deduce the order which 1. The beacons flash in the frame of reference of rocket A. So we're looking at the frame of reference of rocket A and we want to know which order these beacons flash. So we want to know where they cut the time axis on the frame of reference A. And to do that, we basically need to take our ruler and draw parallel to this x-axis. We need to draw where they hit the time axis. So we're going to draw parallel like this. And where these events sit on the time axis, parallel like this. So once we've done that, we follow up the time axis. So it goes like this. And at this point here in the time axis, X and Y will flash simultaneously. Then later on in the time axis of A, Z will flash. So the answer here is X and Y flash first at the same time. Then Z flashes. B2. Deduce the order which the Earth sees the beacon flash. So we're going into the Earth's frame of reference now, and it sees it. Now, when this beacon flashes, it will emit light at the speed of light. And for that, we have to draw some light cones. So again, I'm just going to take all that off. Right. Let's draw a couple of light cones. Light cones are drawn at 45 degrees in both directions from each flash of light. let's draw a light cone here. Oops. And we're drawing light cones because these flashes of light are emitting light at the speed of light, and this is where they will travel on our space-time diagram. So we've got all our light cones, but remember we're going in the frame of reference now of Earth. So we're going to head up the time axis in our Earth frame of reference. At this point, we'll see X flash first. Then at this point, we'll see both Y and Z flash at the same time, because that's what's happening in the time axis for the Earth. X is observed first. Then Y and Z simultaneously. Question 4. A. Define proper length. Wow, I love a definition question. It's very easy, easy marks. And if you need help memorising your definitions with GradePod, head to Drunk on Definitions. You know I've got you. You know I'm going to help you out with that. Okay, but the definition for proper length is the length of an object in its rest frame B. A charged pion decays spontaneously in a time of 26 nanoseconds as measured in the frame of reference in which it is stationary. The pion moves with a velocity of 0.96 c relative to the Earth. Calculate the pion's lifetime measured by an observer on Earth. Well, if it's stationary, then it experiences proper time. So the proper time of the pion is 26 nanoseconds. It is moving with a speed that is very close to the speed of light, so we are going to have to find out what the Lorentz factor is. So it's 1 minus v squared over c squared, which is 1 over 1 minus 0.96 squared, which gives us a value of 3.57. So we're going to use the time dilation formula. We're going to use T equals gamma T naught. And we know that the charged pion, this time here is in its rest frame, so that is the proper time. So it's 3.57 times 26 nanoseconds, which gives us a value of 92.85 nanoseconds. And let's put that down to 2 significant figures, given that the rest of the data is in 2 significant figures. C. In the pion reference frame, the Earth moves a distance x before the pion decays. In the Earth reference frame, the pion moves a distance y before the pion decays. Demonstrate with calculations how the length contraction applies to this situation. So we're going to have to demonstrate which is the proper length and which is the contracted length, and then do some calculations. The proper length in this situation is the length experienced on Earth. And how do I know that? Well, if I look at the length contraction formula, I know from my study of pions and muons and so on, the Earth thinks that the pion or the muon travels a longer distance than the muon does. Okay, so I know that L naught in this situation is going to be greater than L because of where the Lorentz factor is. So for me, I know that L naught is the Earth's frame of reference and L is the pion frame of reference. L naught is proper length, and that's experienced by Earth. L is the contracted length, experienced by the pion. The data we've got in the question above gives us the data in the frame of reference of the pion. So we can find out what the distance is using the pion's data, which is distance equals speed times time, which is 0.96 C times 26 nanoseconds, which gives us a value of 7.448 meters. We've done that. And then to find the proper length, we're going to use L0 equals gamma times L from up here. We've got gamma is 3.57 from the question above, times the original length down here, which is 7.448, which gives us a longer length of 26.7 meters. So the Earth experiences it moving 26.7 meters. The Pion itself thinks it only moves 7.448 meters. Oh, actually, let's bring that down to the right number of significant figures. They both need to be at 2 significant figures, don't they? Question 5. A spaceship S leaves the Earth with a speed of v equals 0.8 c. The space diagram for the Earth is shown. A clock on the Earth and a clock on the spaceship are synchronized at the origin of the space-time diagram. A. Calculate the angle between the world line of S and the world line of the Earth. This is the world line of the Earth. And this is the world line of S. The trick here is to draw a triangle. And this is the angle we're looking at. And with that triangle, this is opposite to the angle. And this is adjacent. Now, why do we care about this? Well, we know from our data booklet that tan theta equals v over c, but tan theta also equals opposite over the adjacent. And this relationship in its entirety is actually much more useful than the relationship of just tan theta equals v over c. But let's get back to the question at hand. Calculate the angle between the world line of S and the world line of Earth. So we want to know what this angle is, theta. In this case, we actually have v and c, and we want to know theta. So theta is equal to the inverse of tan v over c. So it's equal to the inverse of tan 0.8 over c, which is the inverse of tan 0.8, which gives us an angle of 0.67 radians or 39 degrees. So theta is equal to 39 degrees. B. Draw on the diagram the x dash axis for the reference frame of S. Okay, well the world line we've already drawn here for S is the CT dash axis. And the x-axis is going to have the same angle of 39 degrees from the x-axis. So we're going to go 39 degrees. Actually, I have a very useful ruler that can do that on here. And we're going to draw it like this. You would use a protractor in the exam to make sure that you have the same angle as your CT dash angle. Okay, so B's done. And C, an event Z is shown on the diagram. Label the coordinates of the event in the reference frame of S. What we do is we plot grid lines that are parallel to our x dash and our CT dash. So we go to x dash, we keep it at 39 degrees. We extrapolate back to the CT dash axis and we extrapolate back to, so keep it at 52 degrees, to the x dash axis. So we have here is the label for the coordinates of the event in x dash, and here is the label for the coordinate in the CT dash axis. That's your answer. Question 6. Identical twins A and B are initially on Earth. Twin A remains on Earth while twin B leaves Earth at the speed of 0.6 c for a return journey to a point 3 light years from Earth. A. Calculate the time taken for the journey in the reference frame of twin A as measured on Earth. So we actually touched on this earlier. Remember I said it's useful to always think of these twins. So we've got twin A stays on Earth, twin B travels away at a speed of 0.6 c, goes away 3 light years away and comes back again. On Earth, twin A is measuring time as normal. They are doing time equals distance over speed to measure their time. I think we're going to use that in a second. But it's useful just pointing out here that twin B is experiencing proper time because twin B is measuring the events, the start and finish at the same spatial position according to them. Okay, so A, calculate the time taken for the journey in the reference frame of the twin as measured on Earth. So we want to use time equals distance over speed. Distance is 6 light years. Speed is 0.6 c. And light years is 6 years at the speed of light. So it's years at the speed of light. 0.6 c. These cancel out, so we're left with 10 years. That's how long it takes in the reference frame of twin A. B, determine the time taken for the journey in the reference frame of twin B. Well, we said that twin B is experiencing proper time, and we want to find out what that is. We know that the time that's dilated is experienced by the twin on Earth, and that's 10 years. So we want to use T equals gamma T naught, but we need to find out what gamma is. And I'm using the term gamma for the Lorentz factor, which is this. So the Lorentz factor is 1.25, which means that T naught equals T over 1.25, which is 10 divided by 1.25, which gives us a value of 8 years. C, draw, for the reference frame of twin A, a space-time diagram that represents the world lines for both twins. Okay, so let's draw our space-time diagram here. We have X on the x-axis and CT on the y-axis. It says to draw world lines for both twins, so let's think of twin A first of all. Twin A is in position X, and actually this position is 0 because it's on Earth, and they stay there. So as time passes, they don't move. So the world line for twin A looks like that. Now we're going to look at the world line for twin B, drawn in the perspective of twin A. And what twin A sees is twin B moving away at a constant speed, and then they turn and change direction and they come back, but they're still travelling forward in time. So twin B looks like that. Question 7. An observer P sitting on a train moving at speed v measures that his journey takes a time delta TP. So we have a train like this. We've got somebody sitting on it, and they measure that the journey takes delta TP. An observer Q at rest with respect to the ground measures that the journey takes delta TQ. A, state which of the two time intervals is a proper time. Well, proper time is defined as the time interval between two events as measured in a frame where the events occur at the same spatial position. Same spatial position. So, in what time frame is it P or Q? In what time frame, P or Q, do the events happen in the same spatial position? Well, it's P. And the question A says, state which of the two time intervals is a proper time. I think you only need to do that. B, calculate the speed of the train for the ratio delta TP over delta TQ equals 0.3. Well, what do we have so far? Well, we know that T equals Lorentz factor times T naught. And if we put that into our notation for the question, delta TQ equals Lorentz factor times delta TP. So 1 over gamma equals delta TP over delta TQ, which is this ratio here. So 1 over gamma equals 0.30. We can use that because that means that gamma, and by gamma I'm meaning the term Lorentz factor, equals 1 over 0.3, which equals 3.33 recurring, which equals 1 over square root of 1 minus v squared over c squared. and we need to rearrange for this to find what v squared is. So we're going to square both sides. So 11.111 recurring equals 1 over 1 minus v squared over c squared. And we're going to work through to find out what v is, and you'll work out that v ends up at 0.95 c. Quite a lot of work for 2 marks, but that's how you do that question. C. Later, the train is travelling at a speed of 0.6 c. Observer P, who is on the train, measures the length of the train to be 125 metres. The train enters a tunnel of length 100 metres according to observer Q, who's watching from the side. Show that the length of the train, according to an observer Q, is 100 metres. So we're looking at length contraction. So our length contraction equation is L equals L naught over the Lorentz factor. In this case, the Lorentz factor will have changed because the speed has changed. So let's work that out, which gives us a value of, oh, we've done this before, it's 1.25. So L equals 125 divided by 1.25, which gives us 100 metres. D. According to Q, and the Q is the person watching, there is an instant at which the train is completely within the tunnel. At that instant, 2 lights at the front and back of the train are turned on simultaneously according to Q. The spacetime diagram, according to observer Q, shows events B with the back lights turned on, and event F, the front lights turned on. So this is observer Q's spacetime diagram, and we can see that if we look to where they cross the CT axis, then those 2 events are simultaneous according to observer Q. D1. Draw the time CT dash and the space x dash axes for observer P's reference frame on the space-time diagram. What we're going to want to do here is draw a set of axes like this. But we don't know what angle to put them at yet. So we're going to want to use this equation here. But do you remember earlier in the tutorial I gave you a little exam tip and I said V over C is equal to 1 over the gradient, and I think we're going to use that here. So V is 0.6 c. It told us that was the speed of observer P over C equals 1 over the gradient, which means that the gradient of this line that we're going to draw is equal to 1 over 0.6, which gives us 5 over 3. So to plot this reference frame, we first want to do a line that is up 5, 1, 2, 3, 4, 5, and along 3. That's our CT dash. And then we have to do the same line for the x dash, but it's along 5, 1, 2, 3, up 3, and that's our x dash. And these 2 angles here are the same. D2. Deduce using the space-time diagram which light was turned on first according to observer P. We're going to want to extrapolate back onto the CT dash axis to see where each of these events sit in their time frame. To do that, we want to draw a set of grid lines that are parallel to this x dash axis. So we're looking to stay parallel 30 degrees, and we're going to do that, and then we'll go to B and we'll stay at 30 degrees and we'll draw it through the CT axis like this. Then we'll follow a positive trajectory up the CT axis. We'll see that F happens here all the way up, and then we see that B happens there. So using the space-time diagram, F was turned on first and then B is turned on. That means the light at the front of the train went on first according to observer P. 3. Apply a Lorentz transformation to show the time difference between events B and F according to observer P. So we want to find that. And it does say apply a Lorentz transformation. There are 3 Lorentz transformations, one for the position, one for the time, and one for the speed. We're interested in this. So we're going to head to your data booklet, and the Lorentz transformation equation we're looking for is this. This is the time difference in the other reference frame, and the time difference is actually to 0. So we can take that to 0. So we've got T dash equals gamma Vx over c squared. And gamma is our Lorentz transformation. We already know that's 1.25. We calculated that earlier. The speed of the train is 0.6 c. The length we're going to use for x is the length according to the other observers. So that was the observer Q. So that was 100 meters over c squared. So we can cancel out one of those c's. What we have is 1.25 times 0.6 times 100 divided by 3 times 10 to the 8, which gives us a value of 2.5 times 10 to the minus 7 seconds, as proven above. 4. Demonstrate that the space-time interval between events B and F is invariant. So we want to prove the invariant quantity. We need to use this equation here. This is from your data booklet, of course. Delta S equals C delta T all squared minus delta X squared. And we're going to do that for each observer. So for observer P, we have delta S squared equals C times, and we've just calculated the time interval in observer P. That is 2.5 times 10 to the minus 7 all squared, minus the length from observer P, which is 125 squared. That gives us a value of 10,000. Now we're going to do it for Q. Delta S squared equals C times, and the time difference for Q is 0. They happen simultaneously. Minus 100 squared, because that's the length according to Q, and that also gives us 10,000. It's invariant. It's the same. E. A second train is moving at a velocity of minus 0.7 c with respect to the ground. So that just means it's going in the opposite direction to the first train. Calculate the speed of the second train relative to the observer. So this is where we're going to use our u dash. It's the speed of one observer relative to another in a relativistic time frame. And for that equation, we go to our data booklet, and we're given this equation here. Okay, so 0.6 c minus 0.7 c over 1 minus 0.6 c times minus 0.7 c over c squared equals 0.6 c plus 0.7 c. 1 minus plus, because that minus makes a plus, 0.6 times 0.7 c squared over c squared. 1.3 c over 1 plus 0.42. So it's 1.3 c over 1.42, which gives us 0.92 c. Question 8. Muons are unstable particles with a proper lifetime of 2.2 microseconds. Muons are produced 2 kilometers above ground and move downwards at a speed of 0.98 c relative to the ground. For this speed, the Lorentz factor is 5. Discuss with suitable calculations how this experiment provides evidence for time dilation. Okay, so with no time dilation, the distance they travel equals speed times time, which is 0.98 c times 2.2 times 10 to the minus 6 seconds. And that gives us a distance of 646.8 meters. So without time dilation, that's how far they'll travel. With time dilation, and this is us carrying out the calculations they requested, the muon is experiencing proper time, and Earth will experience dilated time. So to find the dilated time experienced due to time dilation, we're looking at 5 times 2.2 microseconds, which gives us 11 microseconds. And that means the distance it can travel before it reaches the end of its lifetime is distance equals speed time, which is 0.98 c times 11 times 10 to the minus 6, which gives us a value of 3234 meters. So we've done two calculations. How does this experiment provide evidence for time dilation? Muons are detected on Earth's surface in a larger volume than expected. Without time dilation, most muons would decay before reaching the surface. Time dilation provides an explanation for the greater number being detected. I think that works.